Welcome students, in this class we will be learning how to use the technique of reducible variable separable methods. Now if you remember, we have already studied about variable separable. They were all straightforward ones. Now this category of variable separable is often denoted as type 2, and the form that we would be looking here is dy over dx is equal to a1 times x positive b1 times y positive c1 divided by a2 times x positive b2 times y positive c2, and the required condition for applying this technique is that b1 positive a2 should be equal to 0. So have that in mind. Now, having mentioned that, let me start out with an illustration. So I've got this question: solve the differential equation which is of the form dy over dx is equal to x negative 2y positive 5 divided by 2x positive 3y negative 1. Now I would be able to apply type 2 only if the coefficient of y, which is b1, and that has to be added with the coefficient of x, or I should say in this case it is 2. This sum should produce me 0. Now if it produces me 0, then I would be able to add, or I would say I would be able to apply this technique. So what exactly is this technique? This technique is simply cross multiplying. That's it. So this is going to be 2 times x positive 3y negative 1 times dy is equal to x negative 2y positive 5 times dx. So this is going to be 2 times x dy positive 3 times y dy negative dy is equal to x times dx negative 2 times y times dx positive 5 times dx. So this is what we have got. Now what we are going to do is we will have to club x times dy. Remember this, x times dy with y times dx. So this is the next step we should do. Always make sure to club x times dy with y times dx. So when this comes, this is going to become positive, and after that you can either move everything to the left or right, it's not going to matter. So I'm just going to rewrite as it is. So 3 times dy negative dy is equal to x times dx positive 5 times dx. So this is what I've got. Now this can be rewritten as 2 times of x times dy positive y times dx. I'm rewriting everything. 3y times dy negative y is equal to x times dx positive 5 times dx. Now what is this? This is nothing but differentiation of x times y, right? Because when you differentiate xy, you're going to apply UV method. If you're going to be applying UV method, this is exactly what you will get, followed by 3 times y dy negative dy is equal to x times dx positive 5 times dx. Now it is imperative for us to know that if I were to integrate dx, I would get x. Of course there's arbitrary constant c. If I were to integrate y, I would get y with an arbitrary constant c. And if I were to integrate d of xy, I will get xy with an arbitrary constant c. So that is what we have to remember. So if I were to be integrating both sides, so what happens when we integrate both sides? So this is going to be 2 times integral d of xy, 3 times y times dy, integral dy is equal to integral x times dx positive 5 times integral dx. Now this is going to give me 2 times xy, this is going to give me y squared, this is going to give me y This is going to give me x squared over 2, and this is going to give me 5x. Of course, there should be an arbitrary constant positive c. Now, this is going to be y squared over 2. So that is critical. We need to make sure that we divide, because of the fact integral x power n dx is x to the power of n positive 1 divided by n positive 1 positive c. So this would be the final solution to the question. So this completes our solution, students. We'll move on to the next question. Students, in type 3 we will be using polar coordinates. Now I'm sure that you all are aware of the polar coordinates. The most popular one is the substitution, that x is equal to r times cos theta and y is equal to r times sin theta. Now if I were to take this substitution, then clearly I know that x squared positive y squared will be equal to r squared. You can substitute it here. I can show that over here. R times cos theta raised to the power of 2 positive r times sin theta raised to the power of 2, which is rewritten as r squared cos square theta positive sin square theta, which is equal to 1, and so I get r squared. So this is just for your understanding. So clearly we know that x squared positive y squared is equal to r squared. Now if I were to differentiate this, then I would get 2 times x positive 2 times y. Differentiation is with reference to x, so it's going to be 2 times y times dy over dx is equal to 2 times r times dr over dx. So this is what we would be getting. Now I can clearly cancel the 2 that you see here, and that would give me x positive y times dy over dx is equal to r times dr over dx. Now if I were to multiply both sides by dx, right, then I would get, this is going to be x times dx positive y times dy is equal to r times dr. So this is a very important differential equation result that we would be using, so have that in mind. This is a very important result. Now also, this is case 1. Now if I were to take case 2, okay, let me just take case 2. Now in case 2, what I'm going to do, I'm going to take y over x. So that would mean my y is r times sin theta, my x is r times cos theta, so my r can be cancelled, giving me tan theta. Now if I were to differentiate both sides with respect to x, then I would get u over v form, right? So d of u over v is equal to v times u dash minus u times v dash divided by v squared. So this is just the formula that we have studied. So by this is going to be x times y dash minus y times x dash is 1 divided by x squared, right? Of course, in this case what we can do is we can, in fact, we can just say d over dx, right? So we can rewrite this. Of course, differential of tan theta is going to be secant squared theta times d theta. So this is what we have got. Now I can rewrite this as x times dy negative y times dx is equal to x squared times secant squared theta times d theta, because now since x is equal to r times cos theta, if I were to substitute here, it's going to be r squared cos squared theta times secant squared theta times d theta. Now secant squared theta cos squared theta can be cancelled, giving me r squared times d theta. On the left hand side is going to be x times dy negative y times dx. So this is another important result which we will be using for our work. So using polar coordinates we have achieved two results. Now we would be employing these results to solve the questions. So we've been given this question, we are expected to solve. We have got x times dx positive y times dy is equal to x times of x dy negative y times of dx. Now we have used polar coordinates and we know the following results. So what are the results we know? We know that x times dx positive y times dy is equal to r times dr. This is one result which we just obtained. And the next result, x times dy minus y times dx is equal to r squared times d theta. So this is the next result we have obtained. Now if I were to take this as 1, therefore 1 can be rewritten x dx positive y dy. I can rewrite this as r times dr, and then I can rewrite this x is equal to r cos theta, so I can just substitute r cos theta, but I can rewrite x dy minus y dx as r squared times d theta. So this is what I can do. So this is equal to r cubed times cos theta times d theta and r dr. So this is already in variable separable mode. So this can be rewritten as dr is equal to, I can cancel, I can get rid of an r and an r here. So this is going to give me r squared times cos theta d theta. I can integrate, but prior to integration the best thing is to have brought this r down, right? But of course I will bring it in the next step. So this is going to be dr over r squared is equal to integral cos theta times d theta. I can rewrite this as integral r to the power of negative 2 times dr is equal to integral cos theta d theta. Now if I were to integrate this, this is going to be r raised to the power of negative 2 positive 1 divided by negative 2 positive 1. Integral of cos theta will give me sin theta. Of course I need to add the arbitrary constant c. So if I were to simplify this, this is going to give me r raised to the power of negative 1 divided by negative 1 is equal to sin theta positive c. I can rewrite this as 1 over r with a negative sign, which is equal to sin theta positive c. So this is going to be my solution. Now if the question has got a choice featuring in polar coordinates, then this is the right place to stop. If it is given in Cartesian coordinates, then it is imperative to know that r is equal to root of x squared positive y squared. We have already seen this because of the fact that x squared positive y squared is equal to r squared. So therefore I can write r to be as root of x squared positive y squared. Now coming to sin theta, we need to know that y over x is equal to tan theta. So if you were to draw the triangle, the right triangle, and if this is going to be theta, and if you are going to be placing, this is opposite side, this is adjacent side, this is hypotenuse side, and tan theta is opposite side divided by adjacent side. But this is nothing but y over x. So this is going to be my y, this is going to be my x. If this is y, this is x, this is going to be r. So my r is going to be root of x squared positive y squared. Okay, so much so for that. But we are expected to find sin theta. So therefore sin theta is opposite side divided by hypotenuse side. So which is equal to opposite side is y, my hypotenuse side is x squared positive y squared. This is my sin theta. So taking these values, and if I were to take this as 2, so therefore I can rewrite 2 to be as negative 1 over root of x squared positive y squared is equal to y over root of x squared positive y squared positive arbitrary constant c. So this is the solution in Cartesian coordinates. Thank you, students. We'll move on to the next question. Students, we are given this question: x positive y times dy over dx divided by x times dy over dx negative y is equal to square root of 1 negative x squared negative y squared over x squared positive y squared. Now clearly, whenever they give problems of this nature, we are not going to be approaching this question using the normal variable separable technique. So the best bet to solve this question is to use the polar form. Now with polar coordinates that we have just exposed to, this question is easily solvable. Now all I need to do is to take the LCM. So if I were to take the LCM, I can rewrite this as x times dx positive y times dy divided by dx. And similarly, this is divided by, if I were to take the LCM, this is going to be x times dy negative y times dx divided by dx. Now clearly you can see the dx and the dx can be cancelled, so that would be equal to square root of, I'm going to rewrite this as 1 negative of x squared positive y squared divided by x squared positive y squared. Now I clearly know that, let me write that down, since r squared is equal to x squared positive y squared, we have already studied this, and x times dx positive y times dy, what is that equal to? Now this one we already know, this is equal to r dr, and we also know this is equal to r squared also. X times dy negative y times dx is equal to r squared d theta. So we can box these things. We know this, and we also know this. So if I were to take this as 2, therefore I can rewrite 2 as, in place of this x dx y dy, I'm going to substitute this r dr. In place of this, I'm going to substitute r squared d theta is equal to square root of, this is going to be 1 negative r squared, and this is going to be r squared, right? So clearly I can cancel a r and a r here, so this is going to give me dr over r times d theta. This is equal to root of 1 negative r squared divided by root of r squared. I'm going to use this space here, so I can rewrite this as dr over r times d theta is equal to root of 1 negative r squared. Now root of r squared is going to be r, so I can clearly cancel these two and now apply variable separable. So this is going to be dr over 1 negative r squared is equal to d theta. So integrating both sides, we get, so what happens when you integrate both sides? This is integral. So when you integrate this, this is going to be sine inverse of r, this is going to be theta positive c. But sine inverse of r, now r squared is x squared positive y squared, so therefore r is root of x squared positive y squared. So this is going to be sine inverse of square root of x squared positive y squared is equal to theta. Now let me write that down here. Now since y over x is equal to tan theta, therefore theta is tan inverse of y over x, right? So just take this value and substitute it. Yeah, this is tan inverse of y over x positive c, and this is the final solution for the question. Students, we are given this question, we are expected to solve x dx positive y dy divided by root of x squared positive y squared is equal to y dx negative x dy divided by x squared. Now the left hand side is simple, but in the right hand side we need to do some alterations. So I'm going to take this as 1 and then I'm going to state it. We know that x times dy negative y times dx is equal to r squared d theta. So if I were to take a negative sign out, then I can rewrite this as y times dx followed by x times dy is equal to r squared d theta. Now pushing the negative sign, in fact multiplying throughout by negative sign, I can now rewrite this as y times dx negative x times dy is equal to negative r squared d theta. Now why did I do all this? I did all these things because of the fact that there is a y dx negative x dy present in the given question. So I want to make sure that I got a polar substitution for that particular term. Now we know that x dy positive y dx, maybe I can state that also we know that x dx positive y dy is equal to r times dr. We know that. And what else we know? We know that x squared positive y squared is equal to r squared. So using all this, so we are going to be using all this, and then we are going to be rewriting. Therefore one can be rewritten as, in place of x dx positive y dy, I'm going to substitute r times dr divided by square root of x squared positive y squared is r squared. In place of this is going to be negative r squared d theta divided by x. X is nothing but r times cos theta. So this can be rewritten as r times dr. Root of r squared will give me r, and I get a negative. Now I can cancel a r and a r there, giving me negative r times d theta divided by cos theta. Now an observation, this is actually x squared, right? So that would mean I have a 2 here. So this one would get cancelled off because of the fact that there is 2 there, which I am noticing now. So that one will get cancelled off and then leaving me 2 there. So I can also cancel the r terms that are present here. So giving me dr is equal to negative d theta divided by cos square theta. Now this is nothing but secant square theta, right? 1 over cos squared, you can write that down, since 1 over cos theta is secant theta, so 1 over cos square theta will be secant square theta. So this is secant square theta d theta, and this is my dr. So I will integrate both sides. Integral of dr would give me r, integral of secant square theta would give me my tan theta, and of course arbitrary constant c. Now we know that y over x is equal to tan theta, so I would be using that over here. So that's going to be negative y over x positive c. On the left hand side, x squared positive y squared is equal to r squared. Therefore r is equal to root of x squared positive y squared. So I will be using these two things. So this is going to give me root of x squared positive y squared. So this is my final solution to this question. Thank you, students.